Welcome to this installment of the Deploy IPv6 series. My name is Tim Rooney, Director of Product Management at Diamond IP, and the goal of this series is to break down into bite-sized chunks IPv6 technologies and techniques. In this video, we're going to talk about IP address block management, and this is actually part one of a series where we're going to talk about the motivation in this webinar, and we'll talk about the mechanics in part two, including a demo of some of our IPv6 subnetting tools. And we're actually going to, much of this applies to IPv4 as well, but certainly with IPv6, many people deploying that somewhat in a greenfield type application, many of these techniques will be applicable. So our agenda here is to talk about what do we mean by address blocks first of all. Secondly, what's the issue? What do we have to be concerned about address blocks in the first place? We'll talk about block management strategies, and then finally our pointer to our calculators. So first of all, what do I mean by an address block? Well, an address block is a contiguous set of IP addresses, and the range of the IP addresses is defined by the address length, which in the case of IPv6 is 128 bits, minus the block prefix length. So the particular block you're dealing with, let's say it's a /64 subnet, so it would be 128 minus 64. So the range of addresses in that block is 2 to the 64th. Other blocks can be derived from that block or allocated, or individual IP addresses can be assigned. The block in which individual IP address assignments are made is referred to as a subnet. Now, allocations of these parent blocks allows alignment of your IP space with your routing topology, with source address-dependent routing technologies, security policies, and other IP address-based policies that you may need to implement within your network. And we'll go through a couple of examples of those. We'll try to illustrate how an effective IP address plan can simplify those various steps. So the scope of what we're discussing here is, if we look at the construct of an IP address, this is the IPv6 definition. It's a global routing prefix, which is the prefix you would typically get from your internet registry or your ISP, the subnet field, the subnet ID, and then the interface identifier. So this is really somewhat the host address in IPv4 speak. Now, within the IPv6 specifications, the prefix is n bits, the subnet ID is m bits, and thereby leaving the host identifier as 128, of course, being the full IPv6 address, minus n minus m bits. Now, of the unicast address space that has been deployed so far by the internet, it requires a 64-bit interface ID. So if we go with that limitation, we then have n bits on the prefix, and then 64 minus n bits at the subnet ID, and that's really the focus of what we're going to discuss here. So you basically get a prefix from your ISP or internet registry of a given size of n bits, and then you can basically take that down to a /64, which is going to be your subnet address. So let's take a simple example. Again, let's start with IPv4. Let's say my organization has 3 locations, a headquarters, a branch office, and a retail store. So if I want to interconnect them into a common enterprise network, I would simply deploy a router on each location, some switches, perhaps other infrastructure to support that, interconnect them through a wide area network, either a private service provider network or over the internet. And then I might have also local area networks feeding off of each of those routers, and I might have several of these as well. But just again, to keep it simple, let's go with 3 routers, 3 sites, and I want to allocate my root block of a 10.0.0.0/16. So basically saying my prefix, so to speak, is the first 2 octets there, 10.0, because that's the first 16 bits. And then I'm going to allocate a subnet ID of another 8 bits. So I'm going to allocate basically up to /24, and then that'll leave 8 bits remaining for the interface ID, or in the case of IPv4, the host address. So I'll basically carve out a /24. Let's take the first address, which of course is the 0 address, and then I take the next block, the first number 1 network, let's say 10.0.1.0/24, and then in turn I take the next block, which is .2, and allocate that to my headquarters location. So Here I've just got a simple way to carve up my blocks. I can take my /16, I can actually slice it into /24s and just assign them as I need them. Now you could use a similar approach with IPv6. Let's say I start with a /48. Let's say this is the address I get from my ISP. And if I want to just take that down to /64s, I could do that as well. I could take the 0 subnet, assign it to my branch, the network number 1 to my retail, and then address 2, which is shown in the address 2001 DB8 1A:2. So in this way I can do a very similar approach, whether it's IPv4 or IPv6, and really what we're illustrating is a monotonic allocation here. So I'm taking the address space I get from my ISP, and I'm just going to take that subnet ID between those two fields and just carve it up into equal sized chunks. So in other words, I've got 256 24s in a 16, and then on the IPv6 side I've got 65,536 /64s in a /48. So I can really just, again, go through the process. I can kind of enumerate all of these possible addresses on that block in between, that subnet ID field, and then just list them out and then just assign them as I need to assign them. So if we look at another example where perhaps I've got a larger scale network, in this case instead of just the 3 locations, I've got a regional headquarters in Tokyo, Dublin, and Philadelphia, with the corporate headquarters off of Philadelphia. I've got subtending networks there within each region, each supporting various distribution centers and branch offices. And then I've also got some virtual private networks that I've deployed into various public cloud services. I'm obviously certainly connected to the internet, which I'm going to use my public space for there as well, and then IoT subnetworks. So if I've got some Internet of Things networks that I've got perhaps deployed in the field, and they're coming back into my network through the internet or perhaps directly through a service provider network, that's really what I'm illustrating there. So let's start again with our root IPv6 block, 2001 DB8 1A/48, and let's just take that example we were just reviewing. Let's follow the same process and allocate /64s. So I'll allocate the first one to our regional headquarters in Asia, the second one maybe to our corporate headquarters, the third one to a branch office in the European office, and basically if I just follow that process and allocate monotonically those /64 subnets from my /48, I can end up with a bunch of address space that I've allocated out. I've got subnets everywhere so everybody can get an address. So let's kind of add another layer of complexity here. Let's say, in addition to just allocating space monolithically as I've done here, I also want to introduce source address dependent routing. So this may be the case if you're using voice over your network as well, where you might want to apply policies for, let's say, for example, higher priority queuing. So let's say I want to allocate a separate set of address space because I need to configure my routers to be aware of not only the destination address for routing of a packet, but I also need to look at the source address with respect to how to treat the packet going through the processing of each router along the stage. So here I actually end up with a pair of subnets in each location. And if I look at the implications on my routing tables, in the Asia region, I'm going to end up with 10 routes here, where I've got, I'm basically advertising to the backbone. Okay, I've got these 10 networks that I'm serving that you can get to through me, and you can access them. So each of the routers in the regional headquarters would have a similarly sized routing table. And then in addition to that, each of these routers would require a table to address the source address routing policy. And in this case, looking at the North America region, we end up with 7 entries in each of the 2 buckets, if you will. One for voice low queuing. I've got my voice SATA traffic. I've allocated those. I need to map that into my routing policy. And then likewise with data, whether I need an explicit policy or not is up to your router implementation, but let's say I do in this case, and I explicitly define those policies there. And so you can see that I've got, even for this very modest sized network of a couple dozen sites, I end up with a large amount of routing table information that's being communicated on my backbone as well as each router needs this SADR implementation. At least at the core, each branch office and distribution center can be more restrictive in that regard. But let's take a look at a different approach, a better approach. If you look at hierarchical allocation, this actually promotes aggregation of your address space, so you end up with fewer entries in that routing table and in that SADR table, and we'll illustrate that in just a moment. So the process here is that you allocate in steps or layers in the allocation process, as we refer to it. First to your core routers in the example we'll use, and then we're going to allocate to each router's subtending networks. But before we do that, we're also going to apply a allocation for our SADR differentiation so that we can apply the policies at each core router in a more simple entry fashion. So to illustrate that, let's look at the example again. Let's go back to our base network, start over with our /48. And in this case, instead of now just allocating /64s, I'm actually going to allocate /52s to each of my regional headquarters. So I'm really creating kind of a subpool, or I'm just creating a smaller subnet ID for each of the regions, which feeds up into my /48. So now I'm going to take within each of these /52s, and I'm going to carve out an additional /56, or actually two additional /56. One, and this is the basis of my SADR policies, where I'm going to use one of these networks for my data, kind of the best effort traffic, and then the other for my voice traffic, for example. So I've got two 56s in each of my regional headquarters that I've allocated out of my /52s. You may have more, but here I'm just, again, from some simplicity. And then from each of these /56s, you would then allocate /64s, let's say, unless you had additional layers. But again, for simplicity, we'll just keep it to these two layers here. So if I allocate first from the Asia region, my /64s from my /56, I end up with each site being assigned a /64, and then likewise on the other /56 in each region. I'm just illustrating it in the Asia region just to not spray paint the slide here with loads of networks again. But you kind of get the idea. So you've kind of created this three-step process where I've allocated a base block to each region, and then from that base block, I allocated a block for each of the SADR policies, and then from there, I allocated each site a /64. So let's now look at the implications on the routing table. If our prior Asia routing table had, those 10 entries, now I've just got one. So basically, it's advertising on the backbone network that I've got this /52. Any address within this /52 space, route to me, and I'll take it from here, so to speak. So each of these core routers now just has one routing table entry for reachability. Likewise, our SADR table has just one entry for each of our layers, for data and for voice. So basically, I've now, because I did that sub-allocation in each region, I've now got the ability to simplify the policy entry in my router. So you can see how, in this simple example, we really reduced by tenfold our routing table that we're conveying on the core network there, and on a similar degree with our source address policies that we had to implement there. So you can see how the address plan can definitely have a role in terms of simplifying the implementation of routing policies and security policies on your network. Now, it's very important that you track these address blocks, because we're not just listing all the /64s that are possible from that given ISP prefix. We're now doing this in a structured fashion. So it's important to maintain the hierarchical nature of that. So here I'm representing kind of a list view in kind of a indentation showing for each of the subregions. So my /48, I allocated a /52 to Asia, /56 for Asia data, /56 for Asia voice. And then with each of those, I allocated a /64 for Asia data regional headquarters, Asia voice regional headquarters. And then likewise for Europe and North America, not shown in the chart. So it's just important to maintain this tracking so that should you need an additional subnet, open a new site, add a new application, you've got tracking for that so you don't have overlapping address space unintentionally. So with hierarchical allocation, as we've seen, we can optimize our routing table sizes, keep them very trim. Likewise, with the source address dependent routing policies, whether it's for applications such as voice versus data or for other reasons, that can also be simplified through a proper address plan. It also enables the scoped application of other IP-based policies. So for filtering ACLs, things of that nature, your address plan can play a key role in simplifying entry of those policies as well. Now, if you're following this hierarchical allocation, your maximum number of layers that you can define is going to be basically the subnet prefix length minus your ISP prefix length. So basically that subnet ID field, that 64 minus n, divided by 4. It's actually rounded down, so it's actually a floor of this function. And in our case, we use the slash 48. So that's 64 minus 48 divided by 4 is 4. Now, this divisor of 4 is assuming you're using the recommended nibble boundary allocation, which is basically each hex digit is represented by 4 bits, and assuming your ISP gives you a multiple of 4 in terms of your allocation, which is commonly the case, then you can just allocate the next 4 bits and the next 4 bits. And again, we'll talk about the mechanics in part 2 of this video, but that also, there's several reasons for that, as we'll address in that video. So each of those sub-allocations would contain basically 16 IP blocks if you allocate just one nibble at a time. And of course, it's important to track these block allocations to enforce aggregation and uniqueness. Now, as I mentioned, we offer a number of tools that we talked about earlier. So we've got a business needs assessment. It's more of a qualitative if you need to deploy v6 or not. IPv6 subnet calculator, it's just really an introductory level subnet calculator if you want to just get familiar with IPv6 and hex and how different size subnets can be represented. And then the hierarchical address planner, which we'll demo in part 2 of this video, is a mechanism to allow you to model such a multi-tiered hierarchy as we illustrated in this video. And then the ROI model is just a tool that you can use to help justify the return on investment for your IPv6 deployment. So I hope you found this video helpful, and we look forward to seeing you in part 2.